All right, Chemistry 3111. So we left off with a little bit of an introduction on esters. And so when it comes to preparing an ester, okay, how do you prepare an ester? Well, we're actually going to see that there's a few ways to do it. But one of the first ways that any organic chemist learns how to prepare an ester is to take a carboxylic acid and to treat it with a base. Because you know that if you take a carboxylic acid and you treat it with a strong base like sodium hydroxide, what you're going to end up with after the first step is you're going to get a carboxylate salt, right? So you have that carboxylate ion, which can behave as a nucleophile. So in the second step, if you treat it with a methyl halide or a primary halide, so again, this is the second step, what's going to happen is just an SN2 reaction, and that is going to give you your ester like that. So again, this is the SN2 mechanism right here. So that works really well. There's nothing wrong with this whatsoever. However, we're going to learn some other ways to make esters as well. And one of the most, another very common method for the synthesis of an ester is to use Fischer esterification, okay? And the way we do this is by combining a carboxylic acid and an alcohol and using an acid catalyst. So remember that when you have H plus in brackets, square brackets, that represents your acid catalyst. And so it says here the mechanism is consistent with one that occurs under acidic conditions. Now, if we have an acid catalyst, let's say that this is sulfuric acid or some kind of strong acid like that. Remember that when you combine a strong acid like sulfuric acid and something like methanol, right, the equilibrium is going to lie to the side of the methanol that is protonated and the hydrogen sulfate ion. Okay, right? This is going to have a higher pKa than sulfuric acid, which has a pKa of something like -9. And so this is actually going to be the acid that is present in your reaction mixture. And so that is the acid we're going to use in our mechanism. So take a look at the mechanism here. So let's go through it step by step. You can see there's a lot of proton transfers in here, but the first step is a proton transfer to render the carboxyl group more susceptible to nucleophilic attack. So after we protonate it, we take this carbon from being mildly electrophilic to being extremely electrophilic once it's protonated. So once it's protonated, now it can be attacked by our methanol, and we end up with this intermediate here. Now, we're going to have to do a series of proton transfers to remove a proton off of the oxygen that's attached to our methyl group, and then to protonate one of the hydroxyl groups so that we can lose water as a leaving group in a subsequent step. Then after we lose water, we end up with another oxonium. We do a proton transfer there. We end up with our ester, and we also regenerate our acid catalyst. They leave that out, but we also regenerate our acid catalyst. So it just starts the process all over again. So you can see that one of the keys of this reaction is removing water, because every single one of these steps is in equilibrium for everything. So if we remove the water, that's going to push the reaction forward. And so how do we do that? Well, it says here, first of all, this mechanism has been proven by using isotope labeling of the oxygen. So this is just oxygen 18 instead of oxygen 16. So this is oxygen 18 that they put in this methanol. And then after they do the Fischer esterification, they see that the oxygen ends up in here. So that's proof of the mechanism. But again, how do we remove the water? We use something called a Dean-Stark trap. This is a picture of it here. I don't really have the energy to go through the whole thing, and it's not part of the content of the class. I just put it in here. This is just from Google Images. But the idea is that your reaction is down here, and it's got water in it, but as you heat it, the water goes up this column and then goes up in here to the reaction, or sorry, to the reflux condenser, but then the water goes straight down into this portion right here. So the water gets trapped in here, and the water is going to be more dense than your other solvent. So if you're like, well, the other solvent will be in here too. That's true, but that's going to stay at the top and the water is going to be at the bottom. So you can just open the stopcock and let the water out. Anyhow, that's kind of a Sparks Notes version of how the Dean-Stark trap works. But the bottom line is that it's used to remove water from the reaction mixture. And that's what pushes the reaction forward. So there you go, Fischer esterification. And I'm going to put a big red star on this one. Why? Because this is a very important reaction mechanism. This reaction is tested a lot. So tested, I'll put here, tested by ACS, MCAT, MCAT, DAT, the old PCAT, etc., etc. Those exams love to ask about Fischer esterification. So this is Fischer esterification. So now that we have that, let's go back to a reaction that we actually learned today, okay? I can put here, see earlier today, okay? We talked about taking an acid chloride with an alcohol and pyridine. I went over this mechanism with you in detail. The reason that you put the pyridine in is to clean up or to mop up or to neutralize the HCl. So you end up with the pyridinium hydrochloride, right? So that neutralizes the HCl, so there's nothing there. So again, we covered that in section 20.8 today. Okay, we went over this reaction in detail today. And so now we know 3 different ways to make an ester from a carboxylic acid. The first one that we saw was, let's say you want to make this ethyl ester. So this would be called ethyl benzoate, if we practice our nomenclature. And of course, this is benzoic acid, benzoic acid, like that. The first one was to treat it with a base like sodium hydroxide and then to use ethyl iodide as an electrophile. So that works really well. So we'll put that here. Okay, that's the first one. Then we learned Fischer. So we learned the Fischer esterification. So in that case, we would need ethanol as our alcohol. We'd need a catalytic amount of acid, and then we'll put negative H2O. So that's the Fischer esterification. And the other one that we learned was to proceed through an acid chloride. So that would be a 2-step process. The first step would be to make the acid chloride and then to treat it with, in this case, it'd be ethanol and pyridine to neutralize the HCl. So we got 3 different ways to make an ester. Okay, 3 different ways to make an ester from a carboxylic acid. All right, so with that in mind, what about the hydrolysis of an ester? So before we took the break, I told you, not only do you have to know the Fischer esterification, which is the formation of an ester, right? So just to review, Fischer esterification is when you take a carboxylic acid, okay? Maybe I'll color code it here the way that he does it, okay? Come on, pen. Where is my pen? Hello, pen. There we go. All right. So if we color code it the way he does it, boy, somebody really doesn't want me making notes on that slide. Okay, let me try it again. I'll win, whatever it takes. So we'll put our R in here plus our alcohol. So we'll put here whatever alcohol. So this is going to be R. Okay, so we add those 2 together. So I use my black pen for that. And the way you do that is with a catalytic amount of acid, and then you lose water, okay? So then you can hydrolyze this, okay? You can break the ester apart in base, followed by treatment with hydronium. And this is called the saponification reaction, okay? This is actually how the pioneers made soap. Is what they did is they took animal fat, so I'll just put here fat from an animal, okay? And then the base, they got this from ashes. So you've probably heard of things like soda ash. So they get the ashes, so they would mix the fat up with the ashes and it would hydrolyze it to make the carboxylate, which is essentially what soap is. Anyhow, without getting into all the necessary details there. But the carboxylate, after the first step, I'll use my red pen here, after the first step would look something like this, where you would have the carboxylate, and that's essentially what soap is. Okay, it's just a carboxylate salt of an animal fat, and then they protonate it in the second step. So after treatment with H3O plus, you end up with a carboxylic acid. But again, this is what soap is, and so that's why it's called the saponification reaction. So here's the mechanism. You can imagine that we don't have to protonate in this case because hydroxide is not a weak nucleophile. It's a very strong nucleophile. So we get a nucleophilic attack. And then we lose our alkoxide is our leaving group. And then the alkoxide comes around and it picks up the proton. So at this point, the reaction is not done. This is the step one. This is with the sodium hydroxide, right? Step one. But then in step two, so in step two, you treat it with hydronium, H3O plus, aqueous acid, and that is going to protonate to give us the carboxylic acid. So that's where the carboxylic acid comes from, okay, is you protonate the carboxylate, just like that. So you end up with the carboxylic acid plus your alcohol along the way. All right, so it says here that esters can also be hydrolyzed under acidic conditions. Remember, under basic conditions, it's called saponification. Under acidic conditions, it has no tsatsi name, okay? It's just the hydrolysis of an ester and acid, okay? But the mechanism, if you've never heard me say this before, listen to my words now, is that if you know a mechanism in one direction, so if I go back here to the mechanism of Fischer esterification, if you know the mechanism in this direction, making the ester, that means that if you do the reverse, if you start with the ester and you hydrolyze it, the mechanism in reverse is identical. It's the exact same mechanism. It's based off of something called the principle of microscopic reversibility. So if you know the mechanism in one direction, the mechanism in reverse is just reverse all of the arrows. And that's all it is. I promise you, okay? So if you go over here and you take a look at the mechanism, you'll see that this mechanism is the reverse of Fischer esterification. So we could put here, I'll even write it here, reverse of Fischer is all this is, right? You have a proton transfer to make an oxonium. Now water is going to be in excess. So now we're not removing water, we're leaving the water in. And so water is going to come in as a nucleophile. We do a proton transfer. Now we protonate the alkoxy group to convert it into a good leaving group. You lose your alcohol, not water. You lose an alcohol, you do a proton transfer, and there you go. So you end up with your carboxylic acid, plus, in this case, you end up with your methanol in this specific case. All right. So there you go. So that's the hydrolysis of an acid, or sorry, an ester in acidic conditions. So like I said at the very beginning, I know I'm rifling around here a lot, but I want to try to collect my thoughts and your thoughts too, is that, what did I tell you before we even started recording this? I said you've got to know Fischer esterification, hydrolysis in base, it's called saponification. And hydrolysis in acid doesn't have a tsatsi name. It's just the hydrolysis of an ester and acid, but its mechanism is the exact reverse of Fischer esterification, okay? So that's pretty much what we need to know about esters. Now, if we move ahead, the next functional group that we were going to discuss are, come on, slides. The next functional group that we were going to discuss is amides. But before we get into that, we have to cover a couple more reactions of esters. So it turns out that you can actually form an amide from the reaction of an ester with an amine. And then it ends up forming an amide. It says here, so follow along with me. It says the overall equilibrium favors the amide. Why? Because amides are more stable. They're less reactive than esters. It says here, though, that this particular reaction, so this reaction here, it says the synthetic utility is limited. Okay, this reaction is actually extremely slow. So we'll put here very slow reaction. And so it's actually way more efficient to make the amide from an acid chloride. And so what I mean is it would be more efficient to make the carboxylic acid, so to hydrolyze this, then make the acid chloride, okay, then make the amide. That's actually less time than to do this one reaction. It's so slow. So it's a reaction that we have to know. It's called an aminolysis. Is it useful? Not really, but it is pertinent to us as chemists. Now, this is a reaction that we covered way back in chapter 12. Okay, I actually tested you on this on the chapter 12 quiz. I said, okay, if you take an ester and you treat it with excess lithium aluminum hydride followed by treatment with water or aqueous acid, what do you get? You get a primary alcohol, right? So you get this portion, this primary alcohol, which comes from this part of your ester. And then you also get the other part too, right? You get another alcohol from this portion of the molecule like that. But again, this was covered in depth in chapter 12. Okay, so two alcohols are produced. And this mechanism was also covered way back in chapter 12. Okay, so again, we covered this in chapter 12. So this is review. The first step was a nucleophilic attack by our hydride. We form an aldehyde along the way. So aldehyde. And what happens when you take an aldehyde and you put it in the presence of lithium aluminum hydride? It's going to reduce it all the way down to your primary alcohol. So you start with an ester and you end up with your primary alcohol. And of course, in this case, you'd also end up with your methanol as well. So if you're wondering, is there a way for me to stop at the aldehyde? Right? I showed you how to take an acid chloride and stop at the aldehyde. I showed you how to take an acid anhydride and stop at the aldehyde. Right? We did that using lithium tri-T-butoxy aluminum hydride. Well, we don't use that reagent with an ester. We use something called diisobutyl aluminum hydride. So the name isn't even on here, so I'll scribble it. So it's diisobutyl, right? There's two isobutyl groups, aluminum hydride. Diisobutyl aluminum hydride, we use DIBAH, which is funny because when I was a student, they called it DIBAL, but we're going to use DIBAH, so diba or di. Sometimes they also call it dibal H, so dibal H. It's got a couple of different names, but this is the one that's used in our textbook. Okay, diisobutyl aluminum hydride. So it's a weaker reducing agent, and so after treatment with water. Now, I don't think the water is the best way to do this. And this is one case where I would say hydronium is the way it says it in the 4th edition of the textbook, and that is actually better. It's going to stop at the aldehyde. So again, it's a selective reducing agent. So what else? This is another reaction that we would have covered in chapter 12. So this one is review. When you take an ester and you treat it with excess Grignard, you end up with a tertiary alcohol after treatment with water or hydronium. Either one is fine. Okay, and this is the same mechanism that we saw way back in chapter 12. You add once, you lose your ethoxide as your alkoxide as your leaving group. You form a ketone. Okay, like that. And I actually discussed this step at length in chapter 12 because I said, well, you probably think that's not a good leaving group, and it's not, but you end up forming a ketone, which is stable. So then you get another nucleophilic attack, and then you do a proton transfer. And this could be with water or with H3O plus. Either one is fine, and you end up with your tertiary alcohol. So now that we've got all that information in our brain, let's see if we can try some reactions with esters here. So the first one is taking this ester and treating it with excess lithium aluminum hydride, followed by treatment with water. And I'm going to put here or H3O plus. Either one is fine. And what are we going to get in this case? What we're going to do, if you remember, is we're going to reduce this part down to a primary alcohol, and then we're going to lose this part as a leaving group simultaneously. So what do we end up with? We're going to end up with this alcohol, a primary alcohol, and then we're also going to end up with methanol as well. Now, normally we don't write it like that. We normally write it like this, but then it gets the point across like that. So we're going to end up with these two alcohols. The next one, we're taking our ester and we're treating it with excess ethyl magnesium bromide, followed by treatment with water or H3O plus. And so what's that going to do? It's going to add twice. So we're going to end up with alcohol, but now we're going to have the ethyl group added once, twice, like that. And then we're also going to be left over with our methanol as well, which is going to be liberated in the reaction. The next one, in the first step, we're going to treat it with sodium hydroxide, which is going to give us sodium benzoate. Right? But sodium benzoate is a good nucleophile, so we'll put here benzoate, sodium like that. So then in the second step, we treat it with ethyl iodide. It does the SN2, and you're going to end up with ethyl benzoate in this particular case. So ethyl benzoate. And then the last one is one you got to kind of be careful with, because remember when you have an ester inside a ring, this is called a lactone. A lactone. So this is going to take some careful carbon counting. Okay. So we have treatment with water or hydronium. Now, let's watch. If you look at this reaction, so let me use yellow. Okay. If we study this reaction, okay, and this reaction here, it's the same thing, but the second one in F, the ester is in a ring. So where did we break the bond? We end up breaking the bond right here. So if we redraw the aromatic ring, it's going to look like this. That doesn't change. Oops. And it was something that looks like this. So we have our alcohol that we're going to form here, and that's going to have two of the R groups attached to it, right? And they're ethyl groups, so we have one ethyl group, two ethyl group. Now the other alcohol was lost as a leaving group, but that's still tied to the aromatic ring. So we have 1, 2 carbons, and then this hydroxyl, right? So we're going to have 1, 2 carbons, and then we have our alcohol like that. Not the prettiest drawing in the world, but that is what the final product is going to look like, is something like that. There we go. So that's a little bit of reactions of esters. Let's try another one. Let's try a big old mechanism here. This is a very, 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 did I say very? Extremely important mechanism. This is the hydrolysis of an ester in acid. Again, this is called a lactone, but again, this is just an ester, right? And then we end up with a carboxylic acid and an alcohol. So what's the first step going to be? Could anybody tell me what the first step of my mechanism is going to be? Is it going to be a nucleophilic attack, loss of leaving group, proton transfer, or a rearrangement? I know you guys know. Could anybody tell me what the first step is going to be? We got to break this ring open somehow. Would it be a nucleophilic attack, a loss of leaving group, a proton transfer, or a rearrangement? Anybody know? Yeah, thanks, Erica. It's going to be a proton transfer, isn't it? Yep. It's going to be a proton transfer because this carbon is not nucleophilic enough to be attacked by water, because water is not a strong electrophile. So we have to do a proton transfer, and that's going to convert it into an oxonium ion like this. Here we go. And that now it's susceptible to nucleophilic attack. And so now my water molecule can come in as a nucleophile. I'm just going to draw the condensed structure of water. So we have our water. It looks like this. It's a good nucleophile when you have a powerful electrophile. So now it's going to come in like this. So now we're going to end up with something that looks like this. So we've got our hydroxyl group over here, and we have our oxonium ion. So now what we've got to do is we've got to move the proton from this oxygen over to this oxygen. So it's going to take a series of proton transfers to convert this oxygen into a good leaving group. So the first one is going to remove the proton from our oxonium. So we have water, which is going to pick up that proton. So we're going to pick up that proton. Then we're going to end up with this intermediate. So we have a hydroxyl here and a hydroxyl here. There's 2 lone pairs on this oxygen. So now it can pick up a proton from hydronium. So we'll draw a hydronium, and we'll do a proton transfer to convert it into a good leaving group. So now we've got a good leaving group. Bet your Bobby socks we do. So now it's protonated, it's ready to go, but it's not just going to leave, okay, until you form a double bond. So we're going to end up forming a double bond like this, and then we're going to lose our leaving group. So what's that going to give us? we're going to end up with something that looks like this. So we're going to have a double bond. We're going to have a proton here. We're going to have this hydroxyl, 1, 2. Then we're going to have our leaving group like that. We have our positive charge here. And then, so to get to the final product, I'm kind of running out of space here. Maybe I should have moved this a little bit over to the side. Maybe I should have put it like this. So let me just clean this up a little bit. So I'll put my arrows like this. There we go. So to get to the very last step, what's going to happen is that water is going to come along as a base, and it's going to pick up this proton, and that's going to give us the final product like that. Not my best curved arrow, is it? There we go. So what do we have? We have a proton transfer in the first step. Then we have a nucleophilic attack. We have another proton transfer, a proton transfer. Then we have a loss of leaving group and a proton transfer to round things out and to get us to the end. So to the last page, did you mean this page? Is this what you meant by the last page? Okay. All right, cool. So there you go. So that covers all the reactions of esters. And now we're going to move into amide territory. So it's just like the movie Seven. We cover this one, this one, this one, and now we're on to the amides, which are the least reactive. And if you notice, amides came up in this section, they came up in this section, in this section. And so we've covered a lot of this chemistry already, okay? So there isn't going to be an abundance of new chemistry. Let me show you what I mean. The first reaction, hey, we looked at this in detail, okay, already. It's kind of where we started the lecture today, was taking an acid chloride. And I said the reason why you use 2 equivalents of your amine is because it's used to neutralize the HCl, so you'd end up with a salt, not a bunch of HCl sitting around, which could ruin your final product like that. So this is, let's say, see today. Okay, so we covered this at the very beginning of the lecture today, so nothing new there. But it turns out, and this is something that I didn't go over with you in detail, but an amide can actually be hydrolyzed in strong acid. However, this reaction is really, really slow. Very slow, requires high temperatures. So it doesn't have, isn't the most synthetically useful reaction, but it does work, right? Because here, if you think about pKa's, I mean, here you're hydrolyzing with a strong acid. So this is a strong acid. And this is your weak acid, And so the equilibrium is going to lie to the side of the weaker acid. So once the ammonia is protonated, I mean, the reaction is definitely not going to go in the reverse direction. So not the fastest reaction, but at least it's not reversible. Anyhow, so that's hydrolysis of an amine, or sorry, an amide with aqueous acid. And it says here the products are favored at equilibrium. Why? Because the NH3 group is protonated to give you the ammonium ion, and so it cannot act like a nucleophile. So this is basically what I just said in the last slide. Okay, this cannot, let's say here, cannot be a nucleophile. Never. Okay, it's got a positive charge. That's impossible for that to behave like a nucleophile. Not ever in this lifetime. And so if you take a look at the mechanism, I'm just going to write it right on here for you. Will not ask. Okay, I think esterification and hydrolysis of an ester, an acid, and a base are way more pertinent than this reaction. But this one is kind of like in the same vein, right? You end up with you start with something that is not very susceptible to nucleophilic attack. You protonate it, then it does get attacked by water as a nucleophile. Then you do a series of proton transfers so that you can lose ammonia, and then you just do another proton transfer. So this is actually very similar. So I'm not even going to write it down. I'll just say it's very similar to the hydrolysis of an ester in acid. Very, very similar, virtually identical, okay? And then it says here that an amide can also be hydrolyzed under basic conditions. I bet you could figure out that mechanism without my help too. But it says here the base catalyzed hydrolysis is even slower than when acidic conditions are used. Now, let's take a look. Remember, in the first step, right after the first step, you're going to end up with the carboxylate ion. And so that's why you need step 2, right, which is going to protonate to give you the carboxylic acid. But let's take a look. The first step here is not a proton transfer. It's a nucleophilic attack. Why? Because hydroxide is actually a very good nucleophile. So it attacks. Now you lose amide as your leaving group, and the amide just does a proton transfer to give you the ammonia plus your carboxylate. And then you treat this with H3O plus, and you end up with your carboxylic acid, like that. There you go. Also, if you're wondering, what drives this reaction forward, it's the formation of the carboxylate ion, which helps push this reaction forward. So what else can you do with an amide? Well, it turns out that you can reduce an amide much the same way that you can reduce other groups, like an ester, for example. You use excess lithium aluminum hydride followed by treatment with water or H3O. No, sorry, not treatment with H3O plus. No, that wouldn't work because that would give you the ammonium ion. My mistake. Anyhow, there you go. So it says this mechanism is quite different from others that we have seen in this chapter. And so I don't think there's any mechanism supplied for this reaction whatsoever. But again, you wouldn't want to use H3O plus. Why would that not work? It wouldn't work because in that case, you'd end up with this, NH3 plus, right? You'd end up with the conjugate acid, okay? And you don't want to have that. So you use water in the second step. So now that we have all that unpacked, let's see here. It says predict the major products of the following reactions. I'm pretty sure you guys could do these faster than me. The first one is an acid chloride with ammonia, and that's just going to give you a primary amide. So that would give you the primary amide, which is going to look like this. Plus, we'd also end up with ammonium chloride in this case. The next one is just the hydrolysis of a primary amide. So in that case, you're going to end up with the carboxylic acid, plus you're going to end up protonating the leaving group, so you end up with the ammonium ion, like that. Okay, remember this reaction is irreversible because this can't behave as a nucleophile ever. All right, so those are those. And now that brings us to, I think, the last section of new chemistry, which is the discussion of nitriles. And I'm not going to ask you much about these mechanisms, but nitriles are important functional groups, okay? So this is where you have a nitrile, so a carbon-nitrogen triple bond. And so we've actually seen this reaction previously. You actually saw this in Chapter 7 of Chemistry 3101. If you've forgotten it, it's totally fine. But if you take cyanide, right, cyanide is a good nucleophile. If I write out the whole Lewis structure, it looks something like this, right? It's a really good nucleophile. It can do N, SN2, nucleophilic attack, loss of leaving group, and you end up with your nitrile. So how else can you make a nitrile? So this is something that we've seen before. A nitrile can also be made from a primary amide using thionyl chloride, okay? I've taught this class long enough that I just tell my students, memorize this reaction, that the thionyl chloride converts the primary amide into the nitrile. You end up liberating sulfur dioxide as a gas, so that pushes the reaction forward. Now, there is a mechanism supplied in the textbook, okay? This is the mechanism. I'll just write it on here so you have the evidence. Will not ask this mechanism, okay? You do not have to know this mechanism. The basic idea is that you end up there's a nucleophilic attack, between the primary amide and your thionyl chloride. Then you lose chloride as the leaving group. Then through a series of proton transfers, you end up losing the sulfur dioxide and the chloride ion to make the nitrile. It's not a very long mechanism, but I feel like it's far enough apart from other mechanisms that you have to know in this class. And Fisher is way more important than this would ever dream of being, so you don't have to memorize this whatsoever. Okay? Now, this is another reaction that we talked about when we talked about the halohydrin Let me think here. Sorry, the cyanohydrin. When we talked about cyanohydrins earlier on in the class, we talked about hydrolysis of a nitrile to a carboxylic acid. So if you remember when we discussed cyanohydrins that look like this, okay, we said if you treat this with H3O plus, it converts this into a carboxylic acid. It actually goes through an amide intermediate, and then the primary amide gets hydrolyzed to the carboxylic acid. This mechanism is also covered in the textbook, and again, I'm going to write it here, will not ask. Okay, there's other mechanisms that are much more important than this, and even this mechanism, after all this work, it only shows you the conversion of the nitrile to the primary amide, and then you have to hydrolyze the primary amide to the carboxylic acid. So you can see it's a very, very long mechanism. It's just a lot of proton transfers, but again, I would never ask you that mechanism. Similarly, like you can hydrolyze a nitrile. So again, if we take a look at this mechanism here, so if you take a look, we can take the nitrile and we can hydrolyze it. We'll just put H3O plus and heat. That will give you the carboxylic acid, but you can also do it in base by treating it with sodium hydroxide, and then you end up with a carboxylate, then you protonate with H3O plus. That works too. There's nothing wrong with that. And that mechanism is also shown in here. But again, I'm going to put it on here for your own personal edification. Will not ask this mechanism, okay? All you really need to know is that a nitrile can be hydrolyzed to a carboxylic acid in base or in acid, okay? Either one will work, okay? Just remember with base, it's a two-step process, and with acid, it's a one-step process. And even though the mechanisms are in here, and I think they're relevant, I don't think they're unimportant, but I think we have enough to know already, so I don't ask my students these mechanisms. It could show up on a homework maybe, where you have access to the textbook and you can go back and refer to things and study them or whatever. But again, I don't test my students on this mechanism, and it's not on the ACS final either. So what else can you do with a nitrile? Well, a nitrile is susceptible to nucleophilic attack, and so we can treat it with a Grignard to give us a ketone. So check this out. In the first step, your Grignard attacks, okay, and you end up with this anion here. But then what happens is the anion, when it gets treated with H3O plus, in the next step, what do you recognize? You guys recognize this functional group? Of course you do. That's an imine or a shift base. And you know that when you treat that with H3O plus in excess, you end up with a ketone, okay? And again, I'm not going to test you on this mechanism in this chapter, but that's the general idea here. So again, your intermediate along the way is going to be an imine, and then that gets hydrolyzed all the way to a ketone. One of the worst accidents, if not the worst accident I've ever seen in the lab, and I've seen a couple of bad ones, was a reaction between lithium aluminum hydride and acetonitrile. Acetonitrile is this compound, CH3C. Do better than that. It's this compound here. Made a huge fire anyhow. Yeah, if you take a nitrile and convert it with treat it with lithium aluminum hydride, the hydride adds twice, and then you add water, not H3O plus, because that would give you the salt, okay? And that reduces you all the way down to the primary amine. So those are all the reactions that you have to know for the carboxylic acids chapter. So with that in mind, let's take a look at the first one. The first one, we're starting out with this nitrile, and we're going to reduce it using lithium aluminum hydride. Remember, the second step is water, not aqueous acid. So let's count our carbons carefully. We have 1, 2, 3, 4, 5. So if we have 1, 2, 3, 4, 5, what happens is we reduce that carbon down to a primary amine in the first one. In the second one, we're taking this is called benzyl bromide. Okay, it's a really powerful electrophile. In the first step, you're taking cyanide, and the cyanide is going to displace the bromine. So after the first step, you're going to have this compound where we have one carbon, then we have our nitrile like that. Then in the next step, you're treating it with methyl magnesium bromide. So if I draw this out explicitly, In the next step, you're treating it with methyl magnesium bromide, which is our Grignard. That's going to do a nucleophilic attack like this, and that is going to give us this intermediate. So let me just draw it like this, okay, where we're going to have our negative charge like this, and there's our methyl group. And then you know that after proton transfer, we're going to convert that to the Schiff base or the imine, okay, and then it's going to get hydrolyzed even further. So this is 1 and 2 is after H3O plus. This isn't the full mechanism, but then the imine is going to get hydrolyzed down to the ketone like that. Okay.